Hi everyone, I'm Cindy, and I'll be sharing with you our project on perceptual biases in icon arrays. This work is done in collaboration with some wonderful people, Ellie, Çağatay, Jake, and Dan. How should you communicate risks and probabilities? Say you're trying out a new medicine. You want to know what the chances are that you will get an allergic reaction. What's the best way that information can be communicated to you so you can truly understand your risks and make an informed decision? I could show it to you via a number, or visualize it for you in a chart. But recent work has shown that conveying probabilistic information using percentages, like 25%, or using charts that depict proportions on a continuum, makes it difficult for people to truly grasp what those proportions mean. On the other hand, using natural frequencies, like 1 out of 4, or using icon arrays tend to elicit more optimal statistical inferences from people and increases numerical comprehension. Recently, data journalists have created what we call risk theaters to communicate projected election outcomes in order to help people make more informed decisions about whether they should go vote or not. These risk theaters help people better grasp the concept of uncertainty by showing polling probabilities as seats in a theater. These seats are randomly colored in two colors, say blue and red. The colors represent the probability that one of two candidates would win an election. Red seat represents that candidate A would win the election, while blue represents that candidate B would win. Imagine buying a ticket to the theater. As you find your seat, sitting in a red seat represents the outcome that candidate A has won, while sitting in a blue seat represents the outcome that candidate B has won. This technique helps the viewer experience the election outcome with a given probability and may change the perception of probabilities. But how accurately can a viewer perceive the relative proportions of blue and red seats? Does there exist an optimal way to arrange the seats such that the viewer will most accurately perceive the relative proportions? For example, you could have blue and red seats interspersed like it's shown here, or you can alternate rows of blue and red, or you can arrange all the blue seats to be on one side and all the red seats to be on the other. So this design space of how icons are arranged within an array has remained underexplored. We present a systematic investigation of how spatial arrangements of icons impact viewer perception of probabilities. And in perceptual studies, we typically start our systematic investigation simple, so we can isolate the factor of icon arrangements. So we'll take away the color, and we'll reduce the theater layout to something simpler, say a 10 by 10 square. This design makes estimating proportions slightly easier than the risk theater, and will likely make our results more conservative. If people are biased when estimating proportions in this square, the bias will likely be exaggerated when they view more complex visualizations. We'll show participants these icon arrays and ask them to estimate the depicted proportion. So we can create a model where you input an icon array depicting a certain proportion and output a prediction of what proportion a human viewer would see in it. This will allow us to inform the design of icon arrays to help people see proportions in the most accurate way. We surveyed existing literature for different ways icon arrays have been spatially arranged. To explore additional possibilities in this space, we also asked students in the data visualization class to draw different ways of arranging icon arrays. We synthesized what we saw into 6 categories of common arrangements, as shown here. In the top condition, icons are filled starting from the top left corner. In the row condition, icons are filled in alternative rows, starting from the leftmost row. Once every other row is filled, the previously skipped rows get filled. In the diagonal condition, icons are filled from the top left corner, expanding diagonally towards the bottom right corner. The central condition fills the innermost layer first and spirals outwards. The edge condition fills the outermost layer first and spirals inwards. In the random condition, black and white icons are interspersed randomly. We showed participants an icon array for 1 second, and then they were prompted to estimate the percentage of filled grids in the icon array via a slider ranging from 0 to 100. Here's what we found. We'll plot the actual proportions people saw on the x-axis and the error in people's estimation on the y-axis. If it's above 0, they overestimated. If it's below, they underestimated. What we found is that people are fairly good with these 3 arrangements on the left. They were fairly accurate. People are less accurate when it comes to the central, edge, and random arrangements. For the top condition, you see there is almost no fluctuation, very little estimation error. Similar story with the row condition. There were some fluctuation here for the diagonal arrangement. The overall accuracy remains high. The average estimation error is within 1%. For the central condition, people tend to overestimate, especially around 60%. For the edge condition, people tend to underestimate, especially around 40 to 50%. For the random arrangement, we observed this interesting science pseudo pattern where participants either overestimated or underestimated depending on the proportion depicted. This pattern is similar to Stephen's power law, which suggests a nonlinear relationship between the perceived and the actual stimulus value. Usually, perceived smaller values tend to be overestimated, while perceived bigger values tend to be underestimated. Here, we see that people perceived values in the 0 to 20 and 60 to 80 range as small and overestimated them, and values in the 20 to 60 and 90 to 100 as big and underestimated them. This is consistent with them using 0 and 60% as reference points in their estimations, and future work can explore the exact mechanism at work. So it's clear that how filled grids are spatially arranged in an icon array can impact viewer perception. You can also use the data collected in our work as a reference tool to help you predict how a viewer might react to an icon array design. Presenting icon arrays with top or row arrangements will help viewers confidently make the most accurate probability estimations. Presenting icon arrays with diagonal arrangement will achieve a similar but less effect in terms of perceptual accuracy. Presenting icon arrays with a central arrangement makes a viewer overestimate the probability, and presenting icon arrays with the edge arrangement makes a viewer underestimate the probability. As for the random arrangement, we demonstrate that the viewers can over or underestimate the probability. Using risk theaters, where filled grids are randomly arranged, may be at the expense of sacrificing perceptual accuracy, despite their other merits. One future research opportunity with these random arrays is to figure out how to construct random grids so that human viewers can veridically perceive the depicted probabilities. This can inform the visualization design to communicate risks. For example, with risk theaters, you can arrange your grids in a way for your viewers to accurately perceive the depicted probabilities. That's all I have. I want to thank all my collaborators for working with me on this, and thank you all for listening.